We know that for the basic sine curve, one period of the graph, that is, one cycle of the graph, occurs from x equals 0 to x equals 2 pi. Now, we want to make a change in the function a little bit and examine the resulting change in the graph. And the change that we're going to make has to do with a coefficient on x this time. Now, consider what we're taking the sine of if we have the sine of bx. You see, we're taking the sine of this value. We can think about it as a real number or as an angle. It doesn't matter. But it's the sine of this value, and it's that value that is going from 0 to 2 pi. That is, one period occurs from a bx value of 0 to a bx value of 2 pi. You see, because that's the angle that we're taking the sine of, or that is the real number that we're taking the sine of. It is bx that we're taking the sine of. All right. And it's that number that moves from 0 to 2 pi to give us that interval over which we have one complete period. Now, what does this lead to? Well, if we solve this for x, we find x to be 0, as we might expect. But over here, when we solve this for x, you see we have 2 pi over b. So our period is occurring from 0 to 2 pi over b for whatever value b takes on. Now, here's how it occurs in a problem. We have y equals sine 2x. Now, the period is from 0 to 2 pi over b, and this needs to be committed to memory. Or we can think about the discussion that led up to it to help remember it. But at any rate, we pop in the b value here, and that's the coefficient of x. And in this case, it's 2. And so we have 2 pi over 2. The 2's go out, and we have pi. So we're going to have one complete period from 0 to pi. Now, in constructing the graph, and I want to compare the graph of this function to the basic sine curve, which is given right here in the dotted as a dotted curve. But we have a complete cycle from 0 to pi. So we have a complete cycle from here to pi. Now, that means that all we need to do to structure the graph is identify those very important points that represent the top of the amplitude, the bottom of the amplitude, and the various intercepts. So we just need to take this interval and subdivide it by splitting it twice. We split it one time here, and this is the point pi over 2. And we split this interval and split that interval, and we have the important positions for the graph. We don't really have to identify the value for that point and the value for this point because we know the nature of the graph. And we know that the sine curve is just going to occur within that interval. So our basic sine curve starts at the bottom of the, at the x-intercept, or we could say the bottom of the, well, it's not the bottom of the amplitude. It's at the intercept. And then we go to the top of the amplitude, and then we go back to 0, and the bottom of the amplitude, and then back to 0. So here is one complete cycle. See, now I could continue the cycle, and I think I will continue it into one more period for this particular function. And it'll have another complete cycle in the next interval that is pi in length, which is right here. And so I'll take that interval, and I'll subdivide it a couple of times. I have a division here. I want to divide these. And now from here to there, I go to the top of the amplitude, back to 0, bottom of the amplitude, back to 0. So now the graph just continues kind of like this. Okay. It appears then that when the value of b is a number larger than 1, it appears to sort of compress the graph this way. It causes the cycle to occur in a smaller interval. And it's also the case that if this is a common fraction, like 1/2 or 2/3 or something like that, it'll cause the cycle to occur over a longer interval. And we want to look at that situation in the next problem.